In this video, we are going to talk about intermolecular forces. Anytime we are thinking about intermolecular forces, we are thinking about interaction between opposite charges in the molecules, which we call them electrostatic forces. And knowing the intermolecular forces can help us to predict or relatively compare some properties in the molecules, such as melting point, boiling point, and solubility. We can divide the intermolecular forces into three categories: dipole-dipole interactions, hydrogen bonding, and dispersion forces. The first interaction is dipole-dipole interaction, compounds that have dipole moment. We talked about dipole moments in the previous videos. These compounds have partially negative and partially positive charge when the molecule is in the liquid phase. Now, for example, consider acetone. Imagine you have a beaker of acetone. That partially negative charge on oxygen arranged in a way to interact with partially positive charge of the carbon on another molecules. And this happens in the solution. We call that dipole-dipole interaction. Now, does this affect the properties of molecules? So if you look at the isobutylene and compare it with acetone, you notice that the melting point and boiling point in acetone are higher than these properties in isobutylene. Why is that? So if you compare these two structures, you notice that in isobutylene we replace this carbon with an oxygen in acetone. Now this causes the isobutylene doesn't have any polar bonds, meaning that the whole molecule is nonpolar. So there isn't any partially negative or partially positive charge in the molecule. However, in acetone, oxygen is more electronegative than carbon. So we have a polar bond in this molecule, which causes the acetone has a strong dipole moment. Therefore, acetone experiences greater attractive interactions comparing to isobutylene, which would be the reason for higher melting point and boiling point in acetone, because we need more energy to break these attractions in the molecule. Hydrogen bonding, which is the strongest intermolecular forces. So when a hydrogen atom is connected to an electronegative atom, such as oxygen, nitrogen, or fluorine, the hydrogen will bear a partial positive charge. So if you have a beaker of water, for example, the hydrogen will be partially positive, and the oxygen, because it's more electronegative, it's going to be partially negative, and we are going to have an interaction between the hydrogen of one molecule with oxygen of another molecule. So this interaction is electrostatic interaction, and we are going to form hydrogen bonding. As I mentioned, hydrogen bonding is the strongest intermolecular forces. And another important thing is the terminology here. We say that we have hydrogen bonding, but actually the hydrogen bonding is not a real bond. It is an interaction, and hydrogen bonding is still much weaker than covalent bond, which is a real bond. So have this in your mind. Also, we have another terminology here, protic solvent. So compounds that are capable of hydrogen bonding, that they can make hydrogen bonding, we call them protic, and we are going to talk about the protic solvents in chapter 7. Let's think about this practice problem. We have propylamine. It has the highest boiling point among these three molecules. Now think about the reason why, what's happening here. Trimethylamine, if you look at trimethylamine, it has an electronegative atom, but there is no hydrogens attached to that electronegative atom. So that molecule cannot make hydrogen bondings in its solution. Now, if you look at ethylmethylamine, it has one hydrogen attached to the electronegative nitrogen, which makes the molecule to be able to make hydrogen bonding in the solution. Now, if you look at propylamine, it actually has two hydrogens attached to nitrogens, meaning more interaction, more hydrogen bondings can happen in propylamine. So the more the interaction, the stronger the interaction would be, and then you need more energy to break that interaction. So the boiling point for propylamine would be higher comparing to the other two. If we have nonpolar molecules, they don't have dipole-dipole interactions or hydrogen bondings, but do they have any intermolecular forces? Do they have interaction with each other? The answer for this question is yes. So what we'll see is that nonpolar compounds have electrons spread out around the nuclei. Here is the example of pentane. We have 1, 2, 3, 4, 5 carbons. We call that pentane. And in the pentane, if you have a pentane solution, there are electrons in this molecule. We know that electrons are found in orbitals and they are not in a certain spot. They are moving around. Sometimes you will see that all electrons will end up at one side of molecule and all the positive charges end up at the other side of the another molecule, and then they will interact with each other. So this is a fleeting interaction and it is the weakest interaction, but these type of interactions can still influence properties such as boiling point in hydrocarbons. Generally, hydrocarbons with higher mass have higher boiling point. Hydrocarbons are molecules that are consist of carbons and hydrogens only. Here we have examples of hydrocarbons: butane, pentane, and hexane. Hexane is heavier than the other two and it has higher boiling point. So why is that? What's happening here? As I explained, hydrocarbons have carbons and hydrogens. So the carbon-hydrogen bond, we know that it's a nonpolar bond. So all of these molecules are nonpolar, meaning that they don't have any dipole-dipole interaction or any hydrogen bonding. The only intermolecular force that we need to consider is London dispersion force. As you add more carbon to the system, to the molecule, the higher the surface area would be for interaction, so the stronger the London dispersion force will get. Therefore, it's harder to break the interaction, and as a result, we are going to have higher boiling point. Now, if you look at the bottom molecules, they all have same mass, but they have different boiling points. And as you can see, the more branch we add to the molecule, the lower the boiling point will get. Why is that? What's happening here? Again, when you have linear or unbranched molecules such as pentane, it's easier to stack the molecules on top of each other, and again, more surface area we are gonna have and higher the London dispersion force will get. But when you add branches to the molecule, you are basically removing that surface area, so the London dispersion force will get weaker and we are gonna have lower boiling point in these molecules. Now look at these 5 molecules and decide which one has the highest boiling point. Remember that hydrogen bonding is always stronger than dipole-dipole interaction, and dipole-dipole is always stronger than London dispersion force. Now looking at these molecules, if you look at molecules C and E, these are the only molecules that have OH bond, meaning that they have hydrogen connected to an electronegative atom, so they can make hydrogen bonding in the solution. And if you compare C with E, you notice that C has a higher number of carbon, so it is heavier than E. Therefore, it's gonna have more London dispersion force than E. So C has the highest boiling point. And then E would have the highest boiling point because it has both hydrogen bonding and London dispersion force. Now, between A, B, and D, D is linear, so we can easier stack the molecule on top of each other. The London dispersion force would be stronger, therefore the boiling point would be higher in D. And if you compare A and B, B is more branched than A, so A would be the next molecule, and the lowest boiling point belongs to molecule B. You heard the term like dissolves like, meaning that if you have a nonpolar molecule, it's gonna dissolve in another nonpolar compound, and polar compound can only get dissolved in another polar solvents or compound. So if you have a molecule that has a dipole-dipole interaction, for example, and if you mix it with another compound that only has a London dispersion force, meaning that it is completely nonpolar, they are immiscible. You cannot dissolve them in each other. So have this term in your mind, like dissolves like, and this is what defines solubility. Let's talk about laundry a little bit. If you only use water to wash your clothes, can you wash off all the dirt out of your clothes with water only? Well, actually, no. So you always need to use soap and water together. Now, why is that? Why do you need soap? If you look at the structure of soap, soap has two parts. It has a polar group and non-polar groups. And the polar group of water, it's hydrophilic, meaning that it likes water. And the nonpolar group of soap, it's hydrophobic, which literally means afraid of water. So water is a polar molecule, we know that. When you put your clothes in soapy water, whatever is polar can get dissolved in water. But the nonpolar dirt, such as grease and oil, will get surrounded by the nonpolar end of the soap molecule to form the structure which we call micelle. Now we have the polar side of the soap out, and the nonpolar side in basically is inside that micelle. So the polar side, using the concept like dissolves like, can easily get dissolved in water, so you can easily get rid of the dirt out of your clothes using the concept of solubility here.